Thank you. So the last thing that I told you guys was the intro to this section, and that was like this. So if I wanted to get a volume of a ream of paper, like how much space it takes up, then I could do it sheet by sheet, like volume of one sheet plus the volume of the next sheet, and combine all those, accumulate all those volumes together, and end up with the volume of the entire thing. And then I said that should sound a lot like what we've been doing with integrals. What we've done in the past is get some sort of height. Oh, shoot. Yeah. Yeah. Oh, my God. This one is not sharpened. I have two, though. Sharpened. Okay. Sorry, let me say that again. What we've been doing with integrals is doing a height times a tiny width. Now, instead of accumulating a bunch of, well, that would give me a bunch of rectangles, height times width. Now, instead of accumulating a bunch of rectangles, I'll accumulate a bunch of three-dimensional objects, a height, a width, and a tiny thickness to end up with a volume. Okay, I hope that makes sense. Thanks, Taylor. All right, so that's a quick reminder of the intro. Here is how you would actually see it, like on a question. This top part just says what I just said. The example one says, let R be the region bounded by the graphs of y squared x equals 9. Find the volume of the solid that has R as its base if every cross section by a plane perpendicular to the x-axis has a given shape. Okay, so we'll talk about what all that means. But here, we're trying to find the volume of the shape made by this. Okay, so this would look sort of like, well, like these are squares all the way down. So it would look something like, that. I'm not very good at drawing, but it kind of looks like this pencil sharpener, I guess, if it came to like a good end point. So it would look like woo, and then stop sharply. Okay, so hopefully you can see the shape. That's the shape we're trying to get the volume of. Obviously, I don't have the formula for this weird three-dimensional object. So what we do is we cut it up into its cross sections and get the volume of each of those. So we cut it up like this, boop, 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 boop. And I mean, it told us that each of those cross sections would be a square. So to get the volume of this, I would accumulate a bunch of squares and add them together. Okay, let me show you what that would look like. I am accumulating a bunch of squares from 0 to 9, and I know that because it told me here's 9, here's 0. Okay, so accumulating from 0 to 9. Okay, now this next part is very, very informal. You won't see this in like college math classes. You won't see this in any other class, but this is how I like to explain it. So don't put this on the AP test or anything like that. But the way I like to explain it is that I'm accumulating a bunch of squares with a tiny thickness. Again, this part right here is like not proper math. This is informal. This is just for explanation purposes. So informal. Okay, so how do I accumulate a bunch of squares? Well, I put the area of the square. That would give me the area of the square times its thickness would give me the volume of each of these tiny squares. Okay, so I'm accumulating. All right, you guys remind me, if this was a square with side length s, what would be the area of that? Okay, yeah, just s times s squared. Very cool. So I just need to find out what each of these squares, like side lengths are, and then put it into the formula. Okay, let's do that. So look at this square right here. Looks like its side length is that. Okay, what the heck? I don't know what that is. But if you make it, like this is kind of abstract, but let me make it 2 dimensions so that it's a little bit easier to digest. Oh, what we have in 2 dimensions is this, 0 to 9. Now, if I cut this anywhere at any x value, boop, right here, this is where I'm cutting it, the square would be coming out of the board like this, boop, boop, boop. That would be the square, okay? And now its base would be this much. Okay, all right, okay. So what is this length? You guys have any ideas? It's kind of out there, but here's a little bit of a hint. Like we'll need the formula or the function for this. It told us that the function is x equals y squared, which we're used to seeing as y equals square root of x is the function. Is that enough of a hint? You have any ideas? Yeah?
You subtract this value to the volume for the.
Okay, what are you thinking? Yeah. Let's subtract the negative.
Or subtract the other. Do one part.
That actually works really well. Yeah, so let me explain. Annabelle is saying, well, this part right here, from the axis to here, is just square root of x. And then she's seeing it like a top minus bottom thing. So this would be square root of x, this would be negative square root of x. You subtract the negative. Yeah, sure. That's a good way of looking at it. The way I explained it to my other class is that from here to here, well, that's just the y value of whatever this x value is. I just chose an arbitrary x, cut the thing. So if this is x, then this length from the axis up to the function is just the y value of the function. In other words, this is just the square root of x. And so this entire thing would be 2 of them. Because one going up, one going back. This is something we've seen before. Like when we were doing normal integrals to get just areas, we said, oh, from the axis up to the function, that's just the y value. This right here would be the y value of this function. Okay. So what I'm saying is the side length of this square is 2 square root of x. Yeah? Should I re-explain it? Okay, all right, I will. But give me a second, let me put this in. We just said that's the side length, just bear with me for now, was 2 square root of x. I'm going to put that into here, 2 square root of x, and I'm putting it into a square. So you guys just told me the area of this square would be base squared. So this is the base, there it is squared, it will be okay. Then from there it's easy, it just turns into a normal integral. So let me go back and try to re-explain this in a better way. And I'm just going to back up and redo it and see if it makes more sense this time. Yeah, I'll just erase all of this with all the dots and everything. Okay. Okay, so in 2 dimensions, this graph, this is a 3-dimensional like Cartesian plane or whatever. If I were to make this 2 dimensions like we're used to seeing, it would look something like this. Okay, now, all along this graph, it has squares coming out of it to make this crazy shape. Whatever that is. Like a quarter of a cheese wheel, it looks like. Okay, so coming out of this is a bunch of squares, boop, 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 out this way. All right, now, what's the base of any one of those squares? Well, let's just get an arbitrary one and get the formula for its base. Okay, so I'm just choosing an arbitrary point. Boop, here's one. I'm calling that x. The square is coming out this way. Okay, and now I'm wondering, what is this length? Okay, well, that's kind of weird to calculate. What's easy to calculate is from the axis up to the function. Okay, if I'm going up from any point up to the function, then that would just be the y value of this function. Like this is just the height from the axis to the function. That's the y value of the function. Like, for example, for a concrete number, like if I was getting the height from here up to here and this was 1, then what would this value be right here? Oh, well, it would just be, well, this is, that's just the square root of x, this guy. So if I want this point on the function at 1, then that would just be the square root of 1. So at any arbitrary x, that would be the square root of x. Yeah, okay, is this making more sense? Okay, so that's just from here to here, and then I have 2 of those. I have one going up, one going down. So 2 square roots of x. Okay, I hope that made more sense. If not, like, it'll keep coming back up. So hold on to your questions if you have them, and it'll make more sense as we do more and more. All right, so that's why I put this in here. That's the base squared, and then dx. All right, now this just becomes a normal thing. 2 square root of x all squared. These just both get squared. It becomes 4, and then x dx. The square root of x squared is just x. All right, and then, okay, now I just integrate this. So this would become, antiderivative of 4x would be 4 times x squared over 2. So just 2x squared. And then you plug in your 9, you plug in your 0. All right, if I plug in 9, I get 81 times 2, which is 162. If I plug in 0, I just get 0. So I don't need to subtract anything more. Okay, so conceptually, this is kind of out there, but you can see procedurally it's not too bad. It's just like an integral. But is there anything I can explain conceptually better? Okay, all right, even if you're like, I don't know what just happened, let's do another one and you'll see what's up. Okay, so this time you're making like same base of the shape, the three-dimensional object, but now when you cut it, boop, 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 you're getting a bunch of rectangles. So your shape looks, I guess, like that, which I don't know what looks like that, like a mouse, I guess. A computer mouse a little bit. Okay, so obviously I don't know the volume for a computer mouse, but I can just cut it up, boop, 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 into a bunch of rectangles, get the volume of each of those, and add them all together. In other words, I'm accumulating, still from 0 to 9, a bunch of rectangles. Again, this is very informal. This is not proper math. But just so you get what's going on, we're accumulating a bunch of rectangles with a tiny thickness. Okay, so what's a rectangle? Well, a rectangle, the area of it would be base times height. Okay, what would be the base, just to make sure you're with me? Yeah, no. Yeah, it's the same thing. I mean, it's the same as this. Still 2 root x. Nice, good job. And then the height of it, it told us was 2. It's a rectangle, the height of 2, it told us was 2. So base times height dx. Okay, all right, okay, you see where I'm getting all these numbers. Okay. All right, and then now it just becomes a normal integral. 2 times 2 is 4, square root of x dx. All right, that's the same thing as 0 to 9, 4 times x to the 1/2 dx. Okay. Then the antiderivative of that would be 4 times, this would become x to the 3/2 by adding 1, then divide by 3/2, or multiply by 2/3, and plug in 9 and 0. Okay, and then let's plug in our things. Let me do two things at once. 4 times 2/3 is just 8/3. And then when I plug in, first of all, when I plug in 0, I'll just get 0. So I'm not even going to worry about that. When I plug in 9, though, I will get 9 to the 3/2. Okay, remember what that means is you take 9, you take the square root of it, and then you cube it. So 9 square root of it is 3, and then cubed is 27, okay. So this x to the 3/2 will become 27. Nice, and then 27 times 8/3. Oh, watch this. 27 divided by 3 is 9, and then times 8 is 72. Okay, so don't let the ugly numbers cloud what just happened. It really wasn't that big of a deal. Your only hard part was figuring out what should be the base, what should be the height, or the height, and then the rest is just normal calculus like you've been doing. Okay, semicircle. I think if you take a second and think about it, you can handle this one. So let me not say much about this semicircle. The only thing I will say is, well, first of all, what's the area of a circle? Because you'll be accumulating a bunch of semicircles. So the area of a semicircle would be what? You tell me, just to make sure that everyone's good. Nice. Okay, good job with the 1/2. Yeah, this should be, okay, pi r squared and then half of that. So your job is to figure out what the radius should be in terms of this, and then integrate that. Okay, try. Okay, how come you said it's very, very close? Okay, what's happened to this, but not even this? Okay, right. And then plus square root of 2, well, not necessarily, like, at some point, yeah, but not for every single one of these. Like, what this will have a way smaller radius than this one. You're getting semicircles all the way across. So, well, it should be square root of 2, but square root of wherever you cut, in other words. Okay, yeah, we're working with it. Similar thing here, your radius shouldn't be a fixed thing. It shouldn't be like a fixed number. It shouldn't have to do with that. Because what I was telling you here is that you're getting semicircles all across it. So this semicircle has a lot smaller radius than this one. What I'm saying is it depends on f. Okay, so if I were to cut any arbitrary one over here, the radius of this would be from here to the function here. Okay, so that's the radius. Yeah. What'd you say? Nice. Then you got this. Okay, nice. But yeah. Nice. What do you say for the radius? What's this? Is this a pi? Okay, then that is like too complicated. Yeah, I see you doing all this calculation, but I see you looking at the right thing. So just be careful. This should be the square root of just x. The radius of any circle, like for example, this one would be from the axis up to here. Oh, well, that's just the y value of this one from here up to the function. So it should just be the radius straight up is square root of x. Oh, yeah. Okay. So if I haven't looked at yours yet, and you're trying to see the answer, a big thing I was seeing with a lot of people is that they had like a fixed number for the radius, but notice, first of all, maybe this wasn't clear, but you're cutting all along this function, and at each point you're getting a semicircle. You're getting a bunch of, like, infinitely many semicircles. And notice that the semicircle over here is way smaller than this one over here. So your radius should be a variable. Okay, and the radius for any particular one of these, so for example this one, would be from the axis up to the function, which we agreed that should be, the radius should just be square root of x, this length right here. Okay, so if you didn't get that, that's what's going on. There should be pi r squared. R we said was square root of x squared over 2 dx. That's for the semicircle. Okay, and then I saw a lot of people finishing, so let me skip the actual integration. Should I? Let's not, okay. Because actually I forgot about this pi over 2 that I want to say something about. You do 0 to 9. Okay, pi over 2, I'm just going to just do that with it. Square root of x squared is just x. Okay, then you see that and you might be like, well, what the heck? I don't know how to anti-differentiate this. But don't freak out. This guy right here is just a constant. So what I like to do is just pull that out. If it's an ugly constant like that, like I don't want to deal with it. So you just do that, like you can pull it out. Okay, and then you anti-differentiate and everything. You get this, you plug in 9 and 0. All right, and then you get 81 for 9 over 4. So 81 pi over 4 minus 0. So 81 pi over 4 altogether. Which I saw a lot of you getting, so really good job. Okay, equilateral triangle, if you're like, if you got this and you did this, then you're a god. But I'm guessing that everyone forgot how to do an equilateral triangle. Like, it's not easy. I had to think about it for a little while. But okay, so the process is still the same. You're getting a bunch of little triangles, getting these all together, and then getting this type of shape. And you want to get the volume of that. Okay, so you're going to be accumulating all these triangles together to add up to the big shape. Accumulating from 0 to 4, the area of an equilateral triangle, dx. Okay, area of a triangle we all remember, I think. What would be the area of a triangle? Did you remember it? Okay, nice. Yeah. Half of the base times the height. Okay, so the base is pretty clear. Just to make sure, what is the base? Okay, thank you. Yeah, it's the same thing we've been talking about. It's this entire length, which we agreed was 2 times the square root of x. The base is easy. Height is the part that's annoying. So let me make an equilateral triangle over here. Okay, then let me remind you some stuff. If it's an equilateral triangle, do you guys remember what each of the angles should be? Yeah? Yes. because they all three need to add up to 180. So 60, 60, and 60. Okay, but I'm going to drop down a perpendicular here because that's what the height is. Okay, you drop down a perpendicular, boop, 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 boop. Now you get that this is 90, that's 60. So looking at this right triangle right here, this would have to be a 30, 60, 90. Okay. And now you could either, if you remember special triangles, sweet, you could figure it out based on that. And my last class said they'd rather do the Pythagorean theorem, so let's do that. 30, 60, 90 triangle, very good, very good. We said this was equilateral, the entire thing. So this like length is the same as this length. And we agreed that the base was 2 square root of x. This part right here is just 2 square root of x. Okay, that's the hypotenuse. Then, special triangles tell us that whatever is on the hypotenuse, the thing across from the 30 should be half of that. So this would be just normal square root of x, like 2 square root of x divided by 2. That's just square root of x. And then here's the part we care about is this part right here, using the Pythagorean theorem, you can get that square root of x squared plus this height squared equals this whole thing squared. Okay, then I'm just going to solve for height, so let me do that fast. This squared is x plus h squared equals this squared is 4x. I subtract the x, I get h squared equals 3x. And so therefore x equals this, or sorry, h equals the square root of 3x. Okay. Okay. So that was side work, but now I can get into the actual integration. So going back to this, we just said that the area of a triangle is half base times height. Base, we said, was 2 square root of x. The height we agreed was this much, the square root of 3x. And then I forgot the 1/2, so let me just put that over 2. And then dx. Nice, and then from here it's just simplifying and integrating. Okay, do you see where all these numbers came from? Should I explain anything again? Nice. Okay, cool. So like I said, now from here it's just simplifying and integrating. I see it 2 divided by 2 is just 1, so cancel 0 to 9. And then let me also do this other thing off to the side. So 2 divided by 2 cancels. I'll leave that off of the next step. Then square root of x times square root of 3x. Remember, that's the same thing as square root of x times square root of 3 times square root of x. Multiplication works, like, plays nicely with square roots. You can split it up like this. And then square root of x times square root of x is just x. So that ends up being just that. Okay, so putting all that together, 2 divided by 2 cancels. Square root of x times itself is just x, and then I still have a square root of 3. The square root of 3 times x. Nice. All right, cool. And then, like I said, whenever I get ugly constants, I just like to pull those out. You don't have to do this. I think it just makes it cleaner, makes it easier to see what you like, what you're integrating and all that. All right, and this is just a straightforward thing. So I go fast through that. Antiderivative of x is x squared over 2. I'm plugging in 9 and 0. I plug in 0, I get 0, so I'm not going to worry about that. If I plug in 9, I get 81 over 2. So I get 81 square root of 3 over 2. Is that what I got here? It is. Okay. That one for sure I wanted to do with you guys. E and F, I think you guys can handle. If you don't remember a trapezoid, when it comes time to it, you can look up here. I'm going to put it here. Remember when we were doing trapezoidal stuff, we learned that it's the height times the first base plus the second base over 2, and that's that. All right, try those two. Try it, try it. You're saying 1/4 f, but it's 1/4 of the length of the base. You have no bit. But you're also the 1/2 I think. That's it. It's slightly off right now. Oh, I know why. Because you said how do you get wow? Wait, I Oh, okay. It would be the same thing, you're right. But be careful because it's not just 1/4. It's about 4 of the length of the base. Oh, yeah. Somebody else in my last grade. And then down here, oh yeah, there's okay, that. What you said, nice. Nice.
Very, very close to it. He's having a shot, so he wants like a shot. Oh. Yeah, we ended up, wait. Yeah, that's what it was. good job, yeah. Okay, good. Nice. Okay, good job, good job. Yeah, you're all right. Good job, you guys. There. Have one. No, you're probably thinking of adding things. Someone else in my office was doing this, where if you're trying to split things up like that, with multiplication, you only need to like count for it once. You don't need to split it up and give everything its own denominator. What I mean is, once these guys cancel, they're both gone. You just have square root guys straight up. Okay, but I do agree with you. Square root guys and square root guys will just be that. Okay, then. Okay, now we've got time for this, and this, and so on that. You should just set it. Okay, yeah. An old quiz. Oh, yeah, I remember. This hurt my heart. That was part of the function. Oh. That was not. That's what I figured. That was what was in there already. Okay, that's how I thought. Yeah, that hurt my heart. And then I think, oh, you're on the 4 or 5 other people out of the 16 quizzes that I graded. 4 or 5 of those people put a P here, but the function itself was just straight up 645. So they should be put a P here. Exactly. Yeah. Okay, I'm gonna put the answers up so you can check them. And then that's where I stopped with fit, and I think that's a good place to stop. Then tomorrow, we can just do it again, and then the rest of the time, like, do the last 2 examples. And then the rest of the time can be for homework. And then just so I have something nice to upload to Schoology, I'm not going to just put them on the DocCam, I'm going to write them all out. So this should have been 0 to 9. I'm going to write it like I have it on my key. You guys may have skipped some steps and simplified in a different way, but you should end up with the same answer. So I have base, kind of far out, base times height is a quarter of that, like times, and then all over 2, the tiny thickness. Then this simplifies to 0 to 9 of 1/2 x. These cancel, these become a half, and these become just x. And then that is a quarter
squared, 9 to 0, or from 0 to 9, and then you plug in a 9, and we get 81/4. That's that one. Which is what I saw most people getting, so good job. And this one, similar thing, if you already got it, you don't need to like listen to me until I get to the answer. But if you didn't get it, here's what's going on. The height it told you was a quarter of the length of the lower base. So a quarter of the length of this is just 1/4 times 2 square root of x. Base 1, it said, is this part. So that's 2 square root of x based on what we've been doing. Base 2 says it's half of that. So half of this is just 1 square root of x. And over 2 because of the formula. Okay, and then I guess I'll just write every step. Then from here, this is half square root of x. This part becomes 3 square roots of x's over 2. Dx. Okay, then watch this. 3 halves times another half is 3/4. Square root of x times itself is just x. And then this becomes 3/4 x squared over 2 at 9 and 0. Plug in a 9, you get 81. Yeah, let's just do it all at once. 81 and then times 3/4 divided by 2 ends up being 243 over 8. Nice. Okay, and then tomorrow we will do this again. We'll do the last two, which will be interesting because they're no longer, the region isn't, it's a new function down here. So you'll have another chance to think about what you should make your basic points. Okay, so tomorrow we'll finish this section.